So in this video, we're going to introduce the fundamental ideals of DC voltage. So before we do that, let's actually talk about DC voltage sources, what they are and what it means. So if I have a circuit in the direction of current, and we haven't formally defined what current means yet, but for now, just view it as the charge that's actually moving in a circuit in some kind of closed loop. If that direction never changes over time, we say that that is direct current. So DC is just an acronym that stands for direct current. That's something that you'll definitely be asked on the exam. So how would I actually find a voltage source? And remember that we're just calling a DC voltage source, just a source of power for our circuit, or what allows it to actually do the interesting things. Where do I actually find them in my day-to-day life around us? Well, anytime that you're dealing with a battery, that is providing a DC voltage. And whenever I have a DC voltage source connected to a circuit, most generally that will produce direct current or DC current. In addition, anytime that you plug something into a wall and you see some type of piece of plastic on the outset, you see this on the actual wall board of your phone where you plug this in. If you feel it getting hot, what it is actually doing is converting the AC power available at your receptacle to DC power. So those are two common sources of DC voltage sources around us in our day-to-day lives. So going back a step, what does it even mean to be voltage? So we know that a DC voltage source actually provides the source of power to our circuit, but what does it mean to have a voltage? So we're all pretty familiar with the ideal of the fact that if I have an object and it has mass, it's going to be attracted to the center of the earth. So imagine I have this cup in front of me and it's at this height. If I move it to a greater height or farther away from the earth, I have to do work in order to move it. So what I would say is that the potential energy of the configuration of this cup at this height versus this height is higher. And we all have some intuition to that. A joke you can make is if you lift a weight in the air, if you're underneath it, if you drop that weight, you know it has potential energy because you can actually feel the kinetic energy that builds up when it actually collides with you, right? It'll hurt. So that's an idea that you know that objects with mass that are elevated from the earth have potential energy. So DC voltage just comes about due to the fact that in addition to objects having this property called mass, they also have a property called charge. But charge actually comes in two flavors, unlike mass, which is always positive. Charge can be positive or charge can be negative. And particles that have a net positive charge, right, if they both have a positive charge, they want to get away from each other. They're repelled. Versus if they have opposite charges, they're attracted. So you can imagine if we have a potential difference between 2 points, say here and here, and I were to take a group of charge in my hand, and I'll define what this is in a minute, but for now, just call it a coulomb of charge, and I move it from one point to another. If I have to do 1 joule of work in order to move it between these 2 points, then I would say that there is a 1 volt potential difference between those 2 points. So that's what the definition of an actual volt is it's if you have a 1 volt potential difference between 2 points, then it would take 1 joule of energy to move 1 coulomb of charge across those 2 points. Now, one of the things that you might notice is that, again, since charge fundamentally is a signed quantity, we can also, just in the same way that we had this kind of idea of potential energy being higher here than here, remember potential energy is always measured between 2 different points. If I measure it from the high point to the low point, it's positive. But if I define it from the low point to the high point, it would be negative. So just know that voltage is a signed or polarized quantity. And if it turns out to be positive, that just means that the point of reference here is higher than the point of reference there. And we'll see that through some examples as well. So that's just the formal definition that I talked about a little bit earlier. But I asked you what would happen if I move the charge the other way. So I said it's a 1 volt potential difference from here to here. If it takes me 1 joule of energy to move a coulomb of charge up the potential gradient, if that coulomb of charge were to move down the potential gradient, well, that's the direction that it wants to go. So I'm not having to do work in that case. I'm actually getting work for free. Work is actually being released here. So what happens in that case is that joule of energy actually comes available to be used by the load in your actual circuit. So that's what it means by work being released from the actual system. So even though DC voltage sources, they look quite different. Just think about all the different batteries around you. They can look quite different in form factor, or those AC to DC converters. They can look different as well. From a modeling point of view in circuit analysis, we're going to want to model it using some type of standardized symbols and standardized relationships. So the first word that I want you to be aware of is this idea of a schematic. And a schematic is nothing more than a way to draw or represent an actual circuit component in a way that isn't dependent on how it actually looks in the real world. It's just a standardized way to draw it. So these two symbols that we see here, these are the ideal schematic symbols for DC voltage sources. And one of the things that makes life confusing is oftentimes, particularly in engineering, there are multiple ways to do the same things. It's just like when we talked about representing vectors in rectangular form, we said there were multiple ways to actually show that vector decomposition. Same thing with schematics. There are two different schematics that are routinely used to represent DC voltages. So one thing that you notice about both of them is they have some reference to polarity in them. There's some plus and minus. And what that means is that if we focus on the top one for now, this node, and node is nothing more than a connection point on a schematic, is higher in potential than the bottom node. Because I have a plus on one side and a minus on another. Same thing down here. If I use the bottom version of the schematic, this node is higher than potential than this node. So when you think about these schematics, these are just the kind of picture representation that are used to actually identify what a DC voltage source is. In addition, when I model something using basic circuit analysis, in addition to the schematic, I need the units and I need the governing equations, and particularly what symbol I actually use to describe that quantity in an equation. So within an equation, whenever I see a DC voltage, I'm going to model it by the actual symbol V. So the symbol V in an equation that involves electrical phenomenon corresponds to voltage. The SI units of a voltage is the unit of volt. And 1 volt is actually defined, as we talked about on the previous slide, as being 1 joule per coulomb. So if I have a battery and it's a 5-volt battery, then it would take 5 joules of energy to move 1 coulomb of charge from the minus to the plus. And all that a DC voltage source does is provide a consistent amount of push across its terminals. So if this is, say, for example, a 10-volt source, what that means is whatever kind of load I connect across it, it's going to continue to provide 10 volts of push in that load, regardless of what kind of load is hooked up. And we'll see that a little bit later. But for now, the one thing you want to definitely remember, the symbol for a DC voltage source, the schematic rather, is one of these two that I've shown here. The symbol within an equation is V, and the units of voltage are volts. So those are the 3 things that you want to take away from this video that I'll definitely have on the homework for this week.